Hello everybody. In this video we will be reviewing some topics revolving around derivatives and how they are used within mathematics. And the topics covered in this video will be finding absolute extrema. We will be doing one graphing exercise, and we will also be talking about the mean value theorem. So without further ado, let's go ahead and begin. So we want to find the absolute extrema for the following function on the given interval. So here is the function you can see on screen already, and the interval that we are working with is 0 to pi. Now, in order to use the extreme value theorem, we just need to check that the function is continuous on this closed interval and differentiable on the open interval 0 to pi. And that is true. That's like asking, is this function continuous? Yes, there are no variables in the denominator. And if we actually go through and find the derivative here, say it'll be f prime of x equaling, let's see, negative sine of 2x plus the square root of 3 cosine of x. Trust me for now, I'll explain this in a second, but if you look here, we will end up with no x's in the denominator either. So since the derivative is continuous on 0 to pi, open interval, we can say that the function, the original function, is differentiable on 0 to pi, the open interval 0 to pi. So since we meet these two conditions, then we are guaranteed to have a max and min on this interval. But in order to figure out where that max and min happens, we need to find any critical values or critical numbers of this function. And so really what we can just do then is set this derivative equal to 0 and solve for x. Oh yes, and how did we get this term here? Well, if you consider the cosine of 2x, this will involve a chain rule when we take the derivative of this, so we would end up with negative sine with the cosine part. Leave 2x inside of that, and then outside back here we would have multiplied by the derivative of this, which is just 2. Well, the 2 that we would have put back here and the 1/2 that we would have had originally in the front would cancel, leaving us with just the negative sine 2x. So now that we've gone over that, I want to do this. If we use a double angle formula here on the negative sine of 2x, we get that the derivative now equals negative 2 sine x cosine x plus square root of 3 cosine x equaling 0. From here, we can common factor a cosine x, and whatever would be left, we can set that equal to 0. So negative 2 sine of x plus square root of 3 equals 0. All I'm doing here is factoring out a cosine, and then I would be left with this on the inside, if you will, if I were writing out the factors. But I just jumped right to setting the factors equal to 0. And if you solve this for sine of x, you get sine of x equals square root of 3 over 2. So now, if we just solve for x here, this would be x equals pi over 2. So there's a critical number. And over here, we would get x equals pi over 3 and 2 pi over 3. So what do? We have to then make sure we check all these critical numbers and the endpoints in the original function. So that means we have to find f of 0, f of pi, those are the endpoints, f of pi over 2, hang one second here, f of pi over 2, there we go, f of pi over 3, and f of 2 pi over 3. And when you substitute all of these values into the original function, you'll see that you get these values here. F of 0 would be 1/2, f of pi would be 1/2, f of pi over 2 would be about 1.23, f of pi over 3 and f of 2 pi over 3 both give you 5 over 4. And so what that means here is we have relative mins, or rather, we have absolute mins here, and we have absolute maxes here. All right, let's take a look at the next example. For this example, we are still finding absolute extrema for a given function on a given closed interval. Now it occurs to me that I misspoke in the last example, saying that the function needed to be continuous and differentiable, but I believe that the function just needs to be continuous. We don't need to worry about differentiability here, and you'll see why here in just a second. So we're going to follow the same process. We need to find the derivative, and by the way, this original function is continuous. There are no x's in the denominator anywhere. So we know this is a continuous function on this interval. Just feel like we need to say that so that we can use this absolute extreme value theorem. So then if we take this derivative, we have 1 minus 2 over x to the 1/3 power, and that's it. The derivative of 4 is 0, so we don't have to worry about that. Now, before I try setting this derivative equal to 0 and solving for x, I need to notice that there is an x in the denominator, and that means we will have a critical number from this denominator. This is where the derivative is undefined. So if I set x to the 1/3 equal to 0 and solve for x by cubing both sides, I will get that x equals 0. So this is one critical number I need to take into account when I start substituting numbers back into the original function. And yes, this 0 is in this interval, so yes, that is absolutely a critical number that we need to pay attention to. All right, so the last critical number here that we need to find is from when we set this derivative equal to 0 and solve for x. So I'm actually going to multiply everything by x to the 1/3. So I can cancel this one here, and we are left with x to the 1/3 minus 2 equals 0. And if I add 2 to both sides and then cube both sides, I will get that x equals 8. And you can like plink this number into a calculator, and it ends up being, I believe, 15 point something. And so 8 here is definitely between -8 and +15. So this is another critical number that we're interested in. So the last thing we need to do then is test all these values. So we just have to find some y values here. So we'll do f of -8 and f of 125 over 8. And these are the endpoints. And then we need f of 0 and f of 8. And these are the critical numbers. And again, when you substitute all these numbers back into the original function, you'll get f of -8 equals -16, f of 125 over 8 equals 7 over 8, f of 0 is 4, and f of 8 is 0. So from this list, how do you pick maxes and mins? I just kind of breezed through that step last example. It's really just pretty simple. You just pick the smallest number in this list, in this case -16. There's your absolute minimum. And the largest number in this list, here's your absolute maximum. Okay, on this slide, we switch over to mean value theorem. First, we have to determine whether the mean value theorem can be used on the given interval for this function. If it can, find all the values of c in the open interval such that this happens. So here is our function. I'm actually going to move that down a little bit so the prompt looks a little clearer. There we go. And this one requires two conditions. So f of x is continuous on -8 to 1. So we need that to happen, and we also need f of x to be differentiable on the open interval -8 to 1. Oops, there we go. So we can just check here. Look at the original function. I don't see any x's in any denominators that will cause any restricted values, holes in the graph, vertical asymptotes, jump discontinuities, nothing like that happening. However, when we take the derivative of this, f prime of x equals 1 minus, now mind you, this is a 1/3 power up here on this x. This would be 1 over 3 x to the 2/3 power. Just by looking at this derivative here, the denominator tells us that f prime of x is undefined at x equals 0. And that's a problem. F of x being undefined at x equals 0 is the same as saying f of x is not differentiable at x equals 0. And why this is a problem is because 0 is in this open interval, and in order for us to use the mean value theorem, we have to have the function be differentiable on the entire interval here. And so since it's not differentiable at 0, we cannot be applied. So the mean value theorem cannot be applied in this situation. How about we take a look at an example where it can be applied so you can know how to proceed after you find that the MVT will work. So a similar exercise to what was being done in the last slide, but now we will have an actual function that is continuous and differentiable on the closed and open intervals respectively. So again here you can see just by looking, no x's in any denominators, so this is continuous on this function, no crazy jump discontinuities, vertical asymptotes, holes in the graph, whatever. And when we look at the derivative, f prime of x, this is 1 plus sine of x. And again, in this case, we don't have any x's in any denominators. So f is continuous on the closed interval here, -pi/2 to pi/2. The derivative is continuous on this interval. Let me write this down. F prime is continuous on -pi/2 to pi/2 open interval. This is exactly equivalent to saying the original function is differentiable on -pi/2 to pi/2, the open interval. So the mean value theorem here will work. So since it works, we need to just tuck this derivative away just for a few minutes, because in order to finish the mean value theorem here, we need to find this other half of our equation. So that's it. Mean value theorem stops right here. Mean value theorem does not help you find these values of C. So what's going to happen now is we have to look here at A and B. So here's A, here's B in the interval. We get these A's and B's from the interval. So I need to find f of b, And really, I don't want to write b. I want to write pi over 2. So f of pi over 2, if I come over here and substitute pi over 2 here and here, I'm going to get pi over 2 minus 0. So this will just be pi over 2. F of a is negative pi over 2. So I'm going to do something similarly over here. And this, if I substitute negative pi over 2 here and here, I get negative pi over 2. So now I can go ahead and fill in everything in this equation, or this fraction here. F of b is pi over 2 minus f of a is negative pi over 2 all over b is pi over 2 minus, oh wow, a is pi over 2. Guys, anytime you are dividing something by itself, you can immediately call it 1. But just to do these subtractions here, we end up with pi over pi. Just to prove it to you, pi over pi is 1. All right, so we've got this side that is here. We've got this side that is here. So what we do is we have to set these two sides equal to each other and solve for x. So that means we will have 1 plus sine of x equal to 1. And once we set these two things equal to each other, we can see that we will subtract 1, gone, so we'll have sine of x equaling 0. And I believe the only place in this interval, actually in the open interval, we're only finding c values in the open interval. The only time that the sign will equal 0 between negative pi over 2 and pi over 2 is when x equals 0. And so that will be our specific answer. For this last slide on this video, we are going to sketch the graph of a function that satisfies the following conditions. So here's a bunch of stuff with the first derivative being positive and negative, and the second derivative being negative and positive, and here's something about the original function. Ooh, we have some stuff here. So this, really quickly, the graph of f is smooth. All that means is that we won't have any cusps or corners or jump discontinuities or vertical asymptotes or holes in the graph. No discontinuities and no places where the function should be not differentiable. It will be continuous and differentiable on our entire graph. Let's see, time to bring up a coordinate plane. Here we go. All right, so what I like to do first is to plot anything about the original function on the graph. So this f of 0 equals 1, that is just a y-intercept, so I'm going to plot that point right here. There we go. Next, I like to do anything involving the first derivative. So the first derivative, it looks like the first derivative is going to change from being positive to negative at -2. So if the derivatives go from being positive, let's just draw it out over here, in the terms of the first derivative test idea. Remember, if we go from the derivative being positive to the derivative being negative, what that tells us about the graph is that the original function is increasing and then decreasing. So increasing to decreasing means we should have some sort of relative maximum over here at -2. So I'm going to put it up here. That way at least we can come down and decrease to get to this point here. Here with the 1, we go from decreasing to increasing. So at 1, I know I should have some sort of relative minimum. Oops, that's 2. Let's make it 1. There we go. So relative minimum, something like right there. So I know the graph is going to have some sort of shape to it that looks like this for right now. Right, something like this. but I don't know exactly how it's supposed to look because I have to take into account what the concavity is here. So I know it's going to be increasing here, decreasing here, and increasing here. So let's do one more thing here. So let's get this graph out of there. Whoops, looks like I lost my minimum. I'm actually going to scoot it up a little bit here. Okay, so now I want to take into account concavity. Now concavity, we can be concave down, but in two different ways, and that's what makes concavity a little weird. We can be increasing in concave down, and we can also be decreasing in concave down. And then we could also be decreasing in concave up and increasing in concave up. So here we have a nice little breakdown of everything that could possibly happen. So these are increasing and these are decreasing, and these over here are concave down and these here are concave up. So when I say these, I mean this row is concave up, this row is concave down. These are increasing, both of them, and these are decreasing, both of those in the columns. So first we are going to be concave, we're going to be flipping concavity here. I'm going to do this in blue. We're going to be flipping concavity here at the blue point. So everything to the left of this blue point should be concave down, and everything to the right of this blue point should be concave up. So let's see what happens here. If I want to be concave down, I guess I'm going to be doing something like this. And that follows what we need with the first derivative too. We're increasing, we are increasing to this point, then we're decreasing. Now I just have to make this concave up, it looks like. So let's go back here. And we know that we are decreasing until this point and concave up. So that is about as good as I can get with where I put the points. Let's just double check here. Is everything concave down to the left of -1? Yes, that part of the graph is opening down. After that, since the concave, the second derivative is positive, we are now concave up. It looks like that part of the graph is opening upward. Cool. Let's see. Are we increasing from -infinity to -2? Yes. Are we also increasing from 1 to infinity? Yes. Are we decreasing everywhere else? Absolutely. We're going down left to right here. The graph is smooth. There are no corners or cusps or any discontinuities. Oh, we need to label any points of inflection and relative extrema. So right here, I have a point of inflection. That is where the concavity changed, and these 2 points right here are relative extrema. And I know those are relative extrema because that is where the function stopped increasing and started decreasing, or vice versa, leaving us with a max or min.